This is lesson 68, VHDL example 42, and in this example we'll write a VHDL program for a 1-bit register. Here's the logic circuit that we developed in the last lesson for a 1-bit register. Remember, we just calculated D using this logic equation. So let's write a VHDL program for this. The inputs will be load, input 0, and clock. We'll also have a clear input. There'll be a clear to this flip-flop that's not shown here. And then we'll take an output Q0. We won't bother with not Q0. So then in the architecture, we've got a signal D and Q, and we just write the logic equation for D from here. So D is just Q and not load, or input 0 and load. And then we'll write our D flip-flop the same way we did back in lesson 64. We have a process with clock and clear. If clear equals 1, we'll have an asynchronous clear, Q0 gets 0. Else, now you remember clock tick event and clock equals 1 means on the rising edge of the clock, then Q gets D. So that's just the behavior of this D flip-flop. And then we'll just set Q0 to the signal Q. And let's simulate it. Here's the clock coming in. We'll use clear, which will clear Q0 asynchronously. And then notice that Q only changes when load is 1. So when load goes 1, then on the rising edge of the clock, the next rising edge of the clock, Q0 gets input 0, which in this case is 1. And then input 0 goes low. Load has gone low, so on this rising edge, Q0 stays there, and Q0 stays 1 until load goes high again. Then on this rising edge of the clock, input 0 is now 0, so Q0 now goes to 0. And it will stay 0 even though input 0 changes because load has gone low. So not until load goes to 1 again. Then on this rising edge of the clock, input 0 is 1, so Q0 goes back to 1. So we see that this simulation in fact produces a 1-bit register. Now we can make the same 1-bit register using our behavioral statement that we had in the last lesson. Here we have the same inputs, load, input 0, clock, clear, and output Q0. But now we don't have to write the logic equation for D and look inside to see the flip-flop. We can just have a process clock and clear. If clear is 1, Q0 gets 0, that's our asynchronous clear. Else, on the rising edge of the clock, remember clock tick event and clock equals 1 means rising edge of the clock, then if load equals 1, then Q0 gets input 0. So this is the behavior of a 1-bit register, and if you simulate this program, you'll find that you'll get exactly the same waveform and simulation that you did for the 1-bit register that we just looked at.